Okay, so now we talk about statements. Okay, so for example, when you say that a sequence of real numbers xn converges to x, okay, this is a statement, correct? However, if my xn's are random variables, okay, so then the statement, okay, needs some more clarifications. That convergence in which sense, okay, because xn's take every n, xn takes various different values for various different sample points. Okay, so this statement would be clarified only if we introduced the notion of or the adjective of the statement. Okay, so that is the thing we are going to do, but before that let us talk about what is random variable, what does it mean. So we start with the measurable function. So if from omega to r is such that if inverse of b is in the Lebesgue sigma algebra for all b in the Borel sigma algebra of R, then you say f is Lebesgue measurable. On the other hand, if I have f from omega to r such that f inverse of b in Borel sigma algebra for all b in the Borel sigma algebra of R, then we say f is Borel measurable. Okay. More generally, okay, so this general setting we would not use much, but more generally, if we have f from omega 1 to omega 2, okay, where omega 1 f1 and omega 2 f2 are two different measurable spaces. These are measurable spaces. Then f is called measurable if f inverse of b2 is in f1 for all b2 in f2. Okay, so that is the definition of measurable functions in the general situation. Okay, so as we would use for this course, which would assume the mathematical model of probability that includes these events would be measurable sets and random variables and measurable functions. So let us write down. So what are the differences? So when you say that A is an event, we mean that A belongs to the sigma algebra. So we have, say, omega fp. Okay, so omega f p is the probability space as we have introduced earlier. So A is an event, that means A belongs to F. Okay, that is the terminology. And we say that P of A, the probability, okay, probability, and that is nothing but measure of A, correct? Measure of A under P. Okay, and what we say that event space, so event space of all events, that is sigma algebra. script f. Okay, and what we say, random variable, so we say x is a random variable, and that means that x from omega to r is a measurable function. Okay, so these are the terminologies. If we say that, we write on this, we say expectation of x, and here we mean that integration of x omega with respect to the measure p. Okay, so this is integration. Okay, so these are the terms and terminologies we are going to use. Okay, now if we have a statement, okay, say for example x is equal to 0, the simplest statement. Okay, but now x is a random variable, is not a real number, real constant, so that is x of omega is equal to 0, but for what? The question is that for all omega, or you have another notion that probability that x is equal to 0 is 1. That means probability of set of all omegas such that x of omega is equal to 0 is 1. So this, if this is the situation, we understand that this situation is weaker than the first situation. This is the first situation, this is the second situation. Okay, so, or in other words, what I want to say is that if, and we call that this part, if this is true, we say x is equal to 0 almost surely with probability 1. So if x is equal to 0 for all omega, that means x is equal to 0 almost surely, but the opposite is not true. Okay, so let us see one easy example, that we consider closed 0 1, and here boil sigma algebra on closed 0 1, and the measure we take the Lebesgue measure, and then we consider x of omega, this random variable is defined as indicator function of 0. So what does it mean? It means that this value is 1 if omega is equal to 0, 0 else. Okay, so this is a very simple function. Okay, so I mean this is only one only at one single point. And if you ask that what is it 0 everywhere? No, it is not 0 everywhere. So this is not falling into the circumstance which is written in the first one, but of course it falls in the second one. Why is it so? Because probability of x is equal to 0 is equal to probability, that means here probability is the Lebesgue measure. So we write down this is Lebesgue measure of the set open 0 closed 1, the points which is between 0 open 0 and closed 1, for that random variable x is equal to 0. But what is the measure of this? The measure of this interval is the length of the interval, that is 1. So this falls into the second category. Okay, so this clarifies this meaning of almost sure statements. Okay, so one can therefore use this. So this all a dot s dot is a small abbreviation of the full form almost surely. Okay, so this acts as an adjective. Okay, for some other statements like xn converges to a random variable x. Okay, this is a set statement. One can also consider the statement, okay, with almost surely. Okay, so with probability 1 it happens. Okay, now we talk about some notions of convergences. So notion of convergence. So we say that xn converges to x almost surely. Okay, so if the probability of events, okay, so here I have probability space omega f p, and my sequence xn as I am discussing here is a function from omega to r, so real valued. Okay, and they are measurable with respect to which sigma algebra? F sigma algebra, correct? They are measurable with respect to F sigma algebra. I am not clarifying what is my F, some abstract sub sigma algebra, abstract sigma algebra, whatever you start with. One can start with the Borel sigma algebra or maybe even smaller than that. Then probability of omega such that xn of omega converges to x. Okay, so this is 1. Okay, so this can also be written in many different ways, like one can ask that, okay, mod of x and omega, the difference, one can talk about the difference. So given epsilon positive, if we consider this difference and ask that when this difference is more than epsilon, since xn converges to x, so of course this difference would after certain time n would be less than given any epsilon. Okay, so if we consider this thing and consider union for all n is equal to capital N to infinity, this is the set, and this set I am taking union capital N to infinity, and whatever I am going to get is dependent on capital N, and then we take capital N is equal to 1 to infinity, and then this whole thing, if that measure is 0, okay, then this is synonymous to the top line. Okay, so this is synonymous of saying the xn converges to x almost surely. Okay, there is another notion of convergence. See, for example, since this set is a decreasing family of sets, we call nested events, and then intersection is there, and probability measure is a finite measure, we can actually take this limit outside, this limit, correct? So outside, so this is synonymous of saying the limit capital N tends to infinity, probability of n is equal to capital N to infinity, the set of events such that x n omega minus x of omega, so this is greater than epsilon, is equal to 0. Okay, however, a weaker version could be, so what is the weaker version? Say, instead of asking the probability of this whole union that goes to 0, we can ask that, okay, probability of only this thing goes to 0. Okay, there is of course a weaker version, because union is the large set. You are saying the large sets, the sequence of the larger, that largest sequence is going to 0. And weaker version is that you do not have this, you just write down limit, this is a weaker version, probability that omega such that mod of xn omega minus x of omega, this is greater than epsilon. Okay, this goes to 0. Okay, this is a weaker version and it has a name. So if this is true, then we say xn converges to x in probability, often we just write down xn and then p above or below this. A short, very short notation, xn converges to x in probability. Okay, so these are the two different notions of convergence we are discussing now. Okay, so next we introduce what is the integration of a measurable function. Okay, that would give me what is expectation, correct? Because in this table we have clarified that if I have a measurable function x and a measure p, and then if we integrate, that would give me expectation of x. Okay, so what do we mean by integration? Okay, for integration theory we should first start with the simplest possible function, and we also give the name as simple function. What is that? So if we have E in the sigma algebra F, so what is the measurable space we are talking about? That omega F, and the measure is P. Okay, so this is the measure space. Okay, this is the measure space we are starting with. Okay, measure space, and then E is in capital F. So the E is in the sigma algebra. So that means E is the measurable set here. That is the definition of measurable set, correct? So a measurable set is nothing but a set which is in the sigma algebra. So I mean, also, you know, I must clarify, it depends on the sigma algebra. So if we change the sigma algebra, the same set may not remain measurable. So always when one says that okay, E is a measurable set, one should also clarify under which sigma algebra this is measurable. Okay, sometimes when we know the choice of sigma algebra, and there is a very immediate default choice, then we sometimes do not mention, we just say that okay, x is measurable. Okay, however, we discuss about various different sigma algebras and confusion may arise. We always clarify that with respect to which sigma algebra this is measurable. If E is in F, that means is measurable, consider a function 1e of omega. So this is a function. So this takes only two values. It takes value 1 when omega is in E and 0 else. So this is of course a measurable function. Why? Because inverse image of 1 is E. E is measurable, and any Borel set you take which includes either 1 or 0, its inverse image would be either E or E complement. If it includes 0 and 1 both, then its inverse image would be omega itself, that is also in the sigma algebra F. If your set B does not include either of 1 and 0, its inverse under 1e would be empty set, that is also in the sigma algebra F. So this 1e is a measurable function. Okay, so this measurable function is called indicator function, is also called indicator function. So this indicator function would be used in the course very often. Okay, I mean this function. Okay, and then if I add two indicator functions, okay, then I would get again another indicator function if that sets are disjoint, correct? So like 1 of E plus 1 of say B would be 1 of E union B only if E and B are disjoint, correct? Disjoint. If they are not disjoint, then it is not going, because that E and B are exactly the same, then you are going to get 2 on that thing. Okay, so here we need to extend the class of indicator functions, because the addition of two indicator functions need not be an indicator function if they are that is indicator only if they are E and B are disjoint. So we consider that collection, we call that simple functions. Okay, simple functions. What are simple functions? Simple functions are nothing but linear combinations of indicator functions. Okay, so finitely many. So if you have that summation of ci 1 of ei I is equal to 1 to n. Okay, so this type of functions, which is finite sum of some constant multiple of indicator functions, then we call that as a simple function. Okay, so this is a simple function. Now for simple function, we would introduce what is the integration of the simple function. Before that, if for indicator function, it is very easy. When we try to, so we go to the next slide. So here we are going to define integration. Okay, first we would define integration for indicator function, then we would define integration for simple function. Okay, for indicator function, integration of 1e, where e is a measurable set, and dp. So this thing is I need to introduce, correct? I need to define. And so whatever way I would define, okay, that should be meaningful in the sense that that should coincide with the purpose of integration. What is the purpose of integration? That integration of a function, of a non-negative function, gives its area under the curve, correct? If you f is a very nice continuous bounded function, non-negative function, and then if you integrate that f on interval 0 to 1, say, okay, finite interval, so then that integration value should be area under the graph of that function. So that is the basic purpose of integration. So if we keep that purpose in our mind, so integration of indicator function of e, so where say if we draw this, say for example this is the real line and e is this set subset of this, indicator function would look like 1 here and 0 outside everywhere, and then area under the function would be exactly this. And then what would be its measurement? So measurement would be this side would be the measure of this base, and the height, multiplication with the height, and height is 1. So the whole area would be 1 into measurement of the base. So it would be exactly measurement of the base, so p of e. Okay, so that is the definition what we get from the purpose of integration. Okay, so we fix it, we keep it, and then for any simple function, if x of omega is simple, then we can write down x of omega as summation finite sum I is equal to 1 to n ci 1 ei of omega, this way from the very definition. And then we also need integration to be a linear functional. Why linear? Because if you have a integration of f and integration of g separately calculated, the integration of the sum of f and g should be sum of their integrations. Okay, so that is true for even area under the curve, that notion. Okay, so here integration of x of omega dp would be summation I is equal to 1 to n ci integration of 1 ei of omega dp. From the definition of integration of indicator function, what we get is that I is equal to 1 to n ci p of ei. So we have now values of integration of in simple functions. Okay,